Hey, welcome back to my Introduction to Mathematical Proofs playlist. We'll be talking about implications. Let's just recap what we talked about over the last two videos. So, in the first video, we talked about axioms, mathematical statements, and universal and existential statements slash quantifiers. And in the second video, we talked about conjunctions, negations, and truth tables. I should remind you, this is all very dense and really hard to think about, and I'm not really sure I did the best job explaining this or a good enough job, right? So if this doesn't make sense, rewatch the videos. You can look at the worksheet. This worksheet is going to be on the bigger side of things. There's going to be lots and lots of questions. And make sure that you're comfortable with all of this. Because yeah, we're talking about formally, okay, what these things are, but then we haven't really been talking much about applying them. So whenever you're actually proving something, oh, how am I gonna apply what I learned when I'm proving something, for example? Because the idea is all of these things that we're learning is a foundation for us to prove things. The big picture is we are developing tools to solve problems, and we're developing how to do proofs. That's the tool we're developing right now. How do we conduct proofs? And there's a few things that I'm probably going to be missing out on that might be mentioned in the worksheets. For example, translating something from pure symbols into pure English and vice versa. That's something that we haven't really been focusing on much. But this is just to introduce you to the idea and get you used to it. Because at the end of the day, it's not really about turning symbols into English. It's about understanding how to do the things that you need to do. But today we're going to be talking about implications. Here's the question that you should be able to do. If x is even, then x squared is even. How would you prove this? Well, we'd assume the if part, or that x is even, then we'd prove the then part, or that x squared is even. And this is called an implication. Some people like to call it an if-then statement. And there's actually a lot going on here, so we'll examine this in detail. And that's pretty much what this video and the next video is going to be about. If something is true, then something else is true. Well, we assume the if, and then try to prove the then. And once again, our best friend truth tables are here. So let x and y be mathematical statements. We don't know whether they're true or false. So we'll write out all the possible values in the table. Then what would if x, then y actually mean? Don't worry about the table being unfinished because we're slowly going to fill it in. We write if x, then y as x and then the two lines and then an arrow going to it, y. So this is if x and y, or x implies y is another way to say it. And we'll slowly go through each case. So if x is true and y is true, what do we know about x implying y? We see that's true. The idea is this. Let's say you have x. If x is true, then you want to show that y is true. And if it is, then the whole entire thing that you showed is true. That's why that implication is true. But now, what if x is true but y is false? Then the whole implication is false. Let's say you assume that x is true, and then you try to show that y is true, but y can never be true because y is false in that case. Then you can never prove this. For example, if x is prime, then 2x is prime. This is false. Because even if x is a prime number, 2x will never be a prime number, so this implication is false. And now this is where it gets really, really annoying with the third and fourth row when x is false. If x is false, it doesn't matter what y is because we never assume that x is true. If x is true, then y, whatever. Well, if x is never true, then the statement doesn't mean anything. There's nothing there. There's no information there at all. There's literally just nothing at play here. So x implies y gives us no information. And we can never disprove the statement because x is never true. If x is never true, how can you disprove that if x is true, then y is true? And this is called vacuous truth. When something is true, not because we can prove it, but because it just can't be false. For example, if lions can fly, then I need to drink water to live. Is this a true statement? Well, lions don't fly, so we can't disprove whether I need to drink water or not. So we can also do another thing. If lions can fly, then I can touch the sun. Once again, lions can't fly, so it doesn't matter if I can touch the sun or not. It doesn't matter. So we say that the implication is true or vacuously true. So that's why the truth table, if x is false, regardless of what y is, we say it's true. And the key takeaway is this. If x is false, then the implication is always true. So we never have to worry about when x is false. The only time we need to worry is when x is true. Then we must show that y is true. Remember, if x is true and y is false, then x does not imply y, which means that it's a false statement. But if we're trying to prove that something is true, when x is true, y must also be true. Then the implication is true. We still have one more thing that we need to cover. Now let's consider the statement right here. If you eat a cookie, I'll nuke Iceland. In our truth table, if you don't eat the cookie, I could theoretically still nuke Iceland and say I didn't lie. And why that matters to me, why does saying the truth matter at all? I don't know. But the idea is this is still technically true in the truth table. Because if you eat a cookie, well, if you don't eat a cookie, that doesn't say anything about if I'm going to nuke Iceland or not. So I can still nuke Iceland. And you're going to be like, well, what? This is just, well, like we agreed on something that the consequence of the eating the cookie was that Iceland becomes Greenland too. This is another way you think about it. You were like, okay, if I eat the cookie, then that'll happen. But if I don't eat the cookie, then nothing will happen. And something deeper is happening. We're implicitly assuming that if you don't eat the cookie, then I won't nuke Iceland. There's a second implication that's actually happening behind the scenes. And that's really annoying because this is a quirk of the English language. And this is why we need this thing called an if and only if, or a double-sided implication. If and only if you eat a cookie, only then will I nuke Iceland. Then I can't nuke Iceland until you eat a cookie, as long as I abide by the truth. And this is not just a simple implication as we just showed. This is a double-sided implication. Or, if you want to use English, we call it an if and only if. So in double-sided implications, we show that X implies Y. So if you eat a cookie, then I'll nuke Iceland. And we'll also show that if you don't eat the cookie, then I won't nuke Iceland. But shockingly, this is actually the same thing. The second condition, not X implies not Y, is the same as Y implies X. Think about this, right? If I nuke Iceland, then that means you ate a cookie. Does that make sense? Assuming that the only time I'll nuke Iceland is when you eat a cookie. If I nuked Iceland, then we know that you ate a cookie. So not X implies not Y is the same as Y implies X. This is really confusing. We'll talk about it a little bit later. But we have to show that X implies Y in the first part. So that's our first thing we need to prove. And then we have to prove the second thing. Usually it's Y implies X, or you can show not X implies not Y. English is what's really making this logic kind of hard to understand. And let's look at an example. Let's say we have an integer a. A is even if and only if, and sometimes people like to write if with two F's. So a, which is an integer, is even if and only if a is not odd. So how would you prove this? Well, first, if a is even, then a is not odd. This should make sense. If a is even, it's 2k, which is not 2k plus 1. So this means that a being even implies that a is not odd. Then we have two methods. Either a is not odd. If a is not odd, then a is even. This is the Y implies X. So if a is not odd, then it's not 2k plus 1, which means it must be 2k, so it's even. Or what you could do is that not X implies not Y. So if a is not even, then a must be odd. So a is not even, so this would be not of the form 2k, so it would be 2k plus 1. Oh, that's odd. And you can do either one to prove the second implication. And interestingly, these if and only ifs act like definitions. So anytime we see X is even, if we replace it with X is not odd, well then everything would still be the same because they literally mean the exact same thing. They have the same truth table. So a definition acts like an if and only if, and vice versa. So let's say you have fact 1, and there's two different ways to represent this fact. Well then, whenever you're proving something, let's say fact 1 implies fact 2, you can use any one of the two representations to prove that fact 1 implies fact 2. And this is really interesting. You're showing equivalence here. Okay, this one was long, so I will see you soon.